In episode 64, titled Scaling Choices, Normalization versus Standardization versus Robust Scaling, the emphasis is on scaling features so models treat them fairly and stably, rather than letting numeric magnitude decide importance by accident. Scaling is often dismissed as a mechanical pre-processing step, but it directly affects how models learn, how fast they converge, and how sensitive they are to noise and outliers. The exam cares because scaling errors can quietly break otherwise sound modeling choices, especially in distance-based methods and gradient-driven optimization. In real systems, poor scaling can make one feature dominate simply because it is measured in larger units, not because it is more informative. When you understand scaling as numeric conditioning rather than data alteration, you can choose the right approach deliberately and explain why it matters. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Normalization rescales a feature to a fixed range, most commonly 0 to 1, so that all values lie within the same bounded interval. This is useful when you want to compare features on a common scale or when a model expects inputs within a specific numeric range for stability. Normalization preserves the shape of the distribution but compresses or stretches it to fit the chosen bounds, meaning relative ordering is unchanged even though absolute spacing is altered. It is often used when features have known minimums and maximums, or when you want to ensure no feature exceeds a certain magnitude. The exam often frames normalization in terms of comparability and bounded inputs, and the correct reasoning is that normalization controls range, not distribution. When you describe normalization clearly, you emphasize that it makes features numerically comparable without making claims about their statistical distribution. Standardization takes a different approach by centering a feature around its mean and scaling it by its standard deviation, producing a variable with mean near 0 and variance near 1. This is useful when a model assumes or benefits from features being centered and having comparable variance, such as many linear models and gradient-based learners. Standardization does not bound values, so extreme values can still appear far from 0, but it aligns features in terms of spread rather than range. The interpretation shifts to thinking in terms of deviations from the average measured in standard deviation units, which can be intuitive for understanding relative magnitude. The exam expects you to recognize that standardization equalizes variance contribution rather than constraining absolute limits. When you explain standardization, you are describing a scale that highlights how unusual a value is relative to typical variation. Robust scaling uses the median and interquartile range instead of the mean and standard deviation, making it resistant to outliers and heavy tails. This approach centers the data around the median and scales based on the spread of the middle portion of the distribution, reducing the influence of extreme values. Robust scaling is particularly helpful when outliers are expected and meaningful, but you do not want them to dominate model training or distance calculations. It preserves relative ordering for most values while dampening the numeric impact of extremes, which can improve stability in skewed or heavy-tailed data. The exam often tests whether you can choose robust scaling when distributions are not well behaved rather than applying standardization blindly. When you describe robust scaling, you emphasize that it conditions numeric input while respecting the reality of extreme cases. Scaling matters most for distance-based models and gradient-based training because these methods are sensitive to numeric magnitude and relative scale. Distance-based models, such as clustering or nearest neighbor approaches, compute similarity directly from numeric differences, so an unscaled feature with large units can dominate distance even if it carries little signal. Gradient-based models adjust parameters based on gradients that depend on feature scale, and poorly scaled features can slow convergence or cause unstable optimization. Scaling helps ensure that no single feature overwhelms learning simply because of its measurement units. The exam often signals this by mentioning distance calculations, optimization difficulty, or slow training, which are cues that scaling is relevant. When you connect scaling to model mechanics, you show that you understand why scaling is not cosmetic but structural. Tree-based models are often less sensitive to scaling because they split on thresholds rather than computing distances or gradients across continuous space. A tree can learn a split on a feature regardless of whether that feature is measured in small or large units because it only cares about order and threshold placement. However, this does not mean scaling is always irrelevant for trees, especially when trees are combined with other components or when regularization and pruning interact with numeric precision. The exam expects you to recognize that tree models are more forgiving of scale, but not to conclude that scaling never matters in mixed pipelines. When you describe this nuance, you avoid the common oversimplification that scaling is unnecessary for trees in all contexts. The key is to match scaling effort to where it materially affects model behavior. A critical discipline is to avoid fitting scalars on test data because scaling parameters learned from the full dataset can leak information about future or held-out observations into training. Even though scaling feels like a neutral transformation, using statistics from the test set changes the distribution seen by the model during training and inflates evaluation performance. The correct approach is to fit scaling parameters on the training data only, and then apply the same parameters to validation, test, and inference data. The exam treats this as a leakage issue, and the correct answer consistently respects the training evaluation boundary. When you explain this clearly, you show that you understand pre-processing is part of the model pipeline and must follow the same discipline as model fitting itself. Scaling does not fix skew, and this distinction matters because it is a common source of confusion. A skewed distribution remains skewed after normalization or standardization because scaling changes units, not shape. If variance increases with magnitude, or if the distribution has a heavy tail, you may need a transformation like a log or power transform before or in addition to scaling. The exam often tests this by describing skewed data and offering scaling as a solution, which is only partially correct if the underlying issue is shape rather than range. A correct reasoning chain separates transformation, which changes shape, from scaling, which changes numeric conditioning. When you articulate this distinction, you demonstrate a deeper understanding of pre-processing roles. Choosing scaling based on model family and data behavior is a judgment exercise that the exam repeatedly tests. If you are using a distance-based method on features with very different ranges, normalization or standardization is usually necessary. If you are using a linear or gradient-based model with roughly symmetric distributions but different variances, standardization is often appropriate. If your data contains heavy tails or frequent outliers that you do not want to dominate learning, robust scaling can provide a safer baseline. The correct choice is rarely always standardize or always normalize, but rather the method that best conditions the numeric space for the chosen model and the observed data shape. When you practice this reasoning, You stop treating scaling as a checkbox and start treating it as part of model design. Once you scale, you must keep scaling parameters stored and applied consistently, because inference time data must be transformed in the same way as training data. Losing or recomputing scaling parameters can silently change input meaning, producing degraded predictions that are difficult to diagnose. This is especially important in production pipelines where data arrives continuously and must be processed identically to training data. The exam often frames this as deployment consistency or reproducibility, and the correct answer includes saving and reusing pre-processing parameters. When you emphasize parameter storage, you are treating scaling as a learned component of the model rather than as a disposable pre-processing step. Scaling assumptions can break as distributions shift, so monitoring drift is part of responsible scaling practice. If the mean, variance, or interquartile range changes significantly over time, the scaled values presented to the model can drift, changing how the model interprets inputs. This does not mean you should constantly refit scalars, but it does mean you should monitor whether the original scaling remains appropriate and whether refitting is justified based on business tolerance. The exam expects you to connect scaling to drift awareness because both are about how numeric representation evolves over time. When you narrate this, you show that scaling is not a one-time decision, but part of ongoing model maintenance. Communicating scaling correctly is important because stakeholders sometimes misinterpret scaling as changing the data's meaning rather than its numeric conditioning. Scaling does not alter order or relative differences in a way that changes the underlying phenomenon. It simply changes the units used for computation. Explaining scaling as conditioning helps maintain trust because it frames the step as a technical necessity for model stability rather than as a manipulation of results. The exam rewards this clarity because it distinguishes sound pre-processing from questionable data manipulation. When you explain scaling plainly, you help others focus on what the model learns rather than how the numbers are formatted internally. A helpful anchor memory is normalize ranges, standardize distributions, robust resists outliers. Normalize is about bounding values to a fixed interval. Standardize is about centering and equalizing variance. And robust scaling is about reducing the influence of extremes. This anchor helps under exam pressure because it maps each method to its primary purpose without requiring detailed formulas. It also prevents common mistakes, such as using normalization to address skew, or using standardization in the presence of severe outliers without caution. When you apply the anchor, you choose scaling based on what problem you are solving rather than on habit. To conclude episode 64, choose one scaling method and defend it for a scenario, because this demonstrates that you can connect pre-processing to modeling needs. Suppose you are clustering users based on behavioral rates and counts that vary widely in scale and include some extreme values, and you want distance calculations to reflect typical behavior rather than being dominated by a few heavy users. Robust scaling is a defensible choice because it centers on the median and scales by the interquartile range, reducing the leverage of extreme cases while preserving relative structure for the majority. This choice improves cluster stability and interpretability without pretending the outliers do not exist, and it aligns with a distance-based method's sensitivity to numeric scale. When you can defend scaling this way, you show exam-ready judgment that connects data behavior, model mechanics, and practical outcomes. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.